just do the same thing that they did the last couple of like 6 years, I think. Like they changed this in 2016 or 2015. So it's still going to be those 3 days before the Thursday of classes, which it kind of sucks because you have 0 time between quals and quarters starting to recover from all the qual studying. But oh well. But hey, at least we know what the exam date and time is now. Okay.
Do they specify what room? I didn't see that in Margarita's email.
It should be the second lecture room in Sky Hall, second floor. I know where it is. I just don't know what the room number is. Because I never have to worry about the room number when I'm in Sky Hall normally. But there's like the big lecture hall, and that's where they're gonna have like the orientations and stuff for first year students. And then there's like the other one, and that's where they normally have the qualifying exams.
Yeah, I haven't been on campus yet, so I'm gonna just stumble around until I find someone to tell me to sit down and take an exam.
I'll be on. I'll be there just to like wish you all good luck before, or at least that's what I'm planning. So at minimum, you could be like, "Where's that nerd?" And then when you find me, I'll show you where the room is. Okay, cool. Or I will ask other people what this room is, or look at my old big class syllabi or something and be like, okay, this class was in this room, and find that syllabi and figure it out. I'll be a detective. Perfect. Yeah, Raoul, you get to sit at the top.
I want to get, I assume you're not allowed in that clock tower, but I really want to go in it.
There are some people allowed in that clock tower because there's a instrument, right? The instrument that's inside the tower, there is somebody that plays that instrument every day at noon. So there is somebody that does get to climb up all of the stairs to get to the top of the clock tower. Okay, so we have
like sorry, on the format of the exam, I just want to make sure I practice like exactly the way it's going to be so I don't psych myself out even more. So like, do you bring in scratch paper, or like do they like have the question and like provide room? Like, are you allowed to bring in like your own pencil and stuff? Like, how does all that work? Just like very briefly.
Yeah, so the only thing that you should bring are pencils and erasers, and they will give you the 3 pages of the exam, right? And it's formatted exactly the same way that I've been formatting mock qual, right? The top block of instructions is the same, and then the part 1 questions and the part 2 questions are on page 2, and the part 3 questions are on page 3. And what they did for me, and I have one here, is they just give you one of these white legal pads, just a fresh one, and they say, here you go, right? So they give you like 100 sheets on a legal pad, and that's how. So you have plenty of scratch paper and paper to turn in your work and things like this.
Is it lined or?
It is lined, yeah. Yeah, you can't see it because.
I know this is so silly. Is it wide rule or college rule? Like.
This is college rule.
Okay, so it's a, and you write just like on one side of each page. Like you don't write on the back.
Yep. Yeah, because why would you write on the back? Right?
Okay, so it's.
Right. You have infinite
pad.
pages essentially, and they have more legal pads than paper. So if for some reason you ran out of paper in your legal pad, yeah, so that is one thing which is different this year than prior years because of COVID restrictions. They're not allowing you to bring food or drink. So like during my exam, I brought like a gigantic bottle of water, or at least I think that they said no food or drink that requires you to take off your mask. So maybe get a water bottle that has like a straw or something so that you can like slip it under your mask if you need to drink something or something like this.
That's weird. They don't allow a snack for like a 3-hour exam, right?
They do normally. I think this year, specifically due to COVID restrictions, they don't want people taking off their masks. So that's why they don't want people bringing in food.
Okay, I may complain about that, like very loudly.
Yeah.
We'll see.
I encourage you all to complain very loudly. It tends to be the only thing that gets the department to do things is when people start complaining
Yeah.
very loudly.
I mean, hopefully we're in a room that's large enough that people aren't biased, because I'll start screaming about that too, right? Like, do you think they're going to do any social distancing? I just really doubt it. You know?
I mean, how many people are taking this exam? What, maybe 12? Like, there's gonna be room between us.
Those rooms
Yeah,
are
I think
tiny
in
though.
268 there will be
The sky
room.
hole rooms are tiny.
I thought, Jacob, didn't you say it was like in a big lecture hall?
It's not, it's the lecture hall, but it's like the
Mhm.
lecture room for math grad students. It's like a slight, it's bigger than a discussion room, but not by much.
That's what I mean.
Are there any other logistics questions? Because these are good questions to ask, right?
Oh yeah, how long does it take to get your like results? Are they like,
Normally about
oh what?
a week.
A week? Okay.
For me, I got mine 1 day earlier than everybody else, but that's because I walked past Wilhelm in the hallway. And he was like, congratulations. I was like, what? And then a day later, the email got sent out. So that was kind of cool. And then I told a bunch of other people in the second year office, and then a bunch of people knocked on Wilhelm's door and bothered him. All right, should we get started with math?
Oh yeah, Jacob, one more question. Do you know who's
Oh,
going to
yeah.
be, I'm sorry if y'all said that already. Do you know who's going to be there proctoring? Is it just
So
one of the dudes?
when I did it, the 3 professors from the course rotated out. So, and yeah, I don't want to say that they did it where like the part A person did it first and the part B person did it second, because I think that it's just arbitrary. But normally the qualifying exam committee splits up that 3-hour proctoring session, so that way they don't have to sit in a room for 3 hours, because why would they do that? They've already taken the balls. So they split up and they proctor an hour each.
Makes sense.
But this depends on committee to committee, right? Sometimes there are people who are on these committees who are like important enough that they're like, I'm not going to do that. And then the other 2 people do an hour and a half each.
Mhm.
Okay, cool. Well, then let's go ahead and get into the math. So 4 people signed up to present problems. Some people signed up to present more than one problem. However, Daly emailed me beforehand and said that she's not going to make it today. So if there are other people that would like to present some of these problems that aren't, that haven't had anybody signed up yet, I will send this back in the chat in case people want to look to see which problems people have signed up for and which problems people haven't. I have solutions for all the problems that people didn't sign up for except for question 8. I just didn't have enough time to get to question 8. And also I was like, I don't need to write a solution for question 8. Question 8 was one of Wilhelm's final exam problems. So that means that, you know, you all should know how to do question 8 by now. So hopefully someone will at least present that one. I don't know if we should just go down the list and start at question 1, or if we should start at question 3, because that's the first one that people signed up for, or if people should be like, hey, can someone talk about this question first, because that was the hard one, or one of the hard ones on the qual. I don't know how y'all want to proceed.
Maybe.
I can do half of one.
Yeah, I say we do the ones that we know, and then we ask you about the ones that nobody or that we have questions on. So if we can go through the ones that we know.
Okay.
We can order in a-
Okay, well, it sounds like that we know something about question 1. So yeah, Raul, if you want to go ahead with question 1.
You're muted, Rahul.
My bad. So yeah, so you have X non-empty, compact, Hausdorff, no isolated points. And I think there's an error. I think you need to also state for when you do this. So it states that you have U is a subset of X is open. I think you also have to require that it's not empty. You want to show that for any U satisfying this condition, there exists, and for any X in X, there exists a non-empty open subset V contained in U such that X is not in the closure of V. X is not in V closure. So the way I did this was I said, well, fix an X, pick for such an X, pick a Y different than X and Y is in U. Since we're in a Hausdorff space, we can find open sets Vx containing X, Vy containing Y, such that Vx intersect Vy is empty. Then, and also those Vx and Vy are open. So then just define V to be U intersect Vy. V is open because it's the finite intersection of open sets. And it is non-empty, and it is clearly contained in U. It's non-empty because Y was chosen to be in U. Moreover, because of this condition, X is not in the closure of V, and we're done with part A. Does that sound good?
Yeah, so all of this is correct. One thing which is probably worth mentioning is that the reason this Y exists in U, which is different from X, is because X has no isolated points, right? U is not an open set consisting of just X, right? Right? Every open set has at least 2 elements in it, so there's always at least an element different from X.
Right. Yeah, and then part B, I wasn't sure how to do. I couldn't think of a clever way to define VNs so that this worked.
I can take over from here if you'd like. So one thing which I will send first for several of these problems, and I'll send this in the chat. I wrote some solutions onto that shared overlay file. So if you click on that overlay file and you go down to mockqual, you click mockqual 3 on the left, click recompile, you'll see that I wrote solutions for several of these problems. So I wrote a solution for question 1. So if you'd like to follow along with my solution as I write things, feel free. Okay, so here's at least how I did this. So we're going to define I'm going to start my natural numbers at 0. It doesn't matter for the problem, right? I'm just adding or subtracting an extra point. Define V0 to be equal to X set minus F of 0. Okay. This is an open set which does not have the image of 0 in it. And then using part A, define Fn as a subset of Fn minus 1 such that Fn is not in the closure of Vn. Okay. So this is exactly right. Like I know that V naught is non-empty, right? Because X can't be a single point, right? Because then it would have an isolated point, right? And similarly, right, none of these V ends can be a single point, right? They always have to have more points in them. And so using part A, we have exactly the condition that we'd like, right? That each of these V ends is non-empty, and for any X, I can choose a smaller open subset, right? Such that the closure avoids a given point, right? So this creates a sequence of nested closed sets, each non-empty. V naught closure contains V1 closure, contains V2 closure, contains V3 closure, contains ... Okay. And since X is compact, the intersection of all of these VI closures, which I will label capital C, is non-empty. But by construction, the image of F is disjoint from C. And I go in a lot more. Oh, yeah, go ahead.
Oh, sorry. Okay, because you're using the finite intersection property, right? So, I mean, maybe it's obvious, but do you have to like explicitly state that like finite collections of intersections are
Well, no,
non-empty?
he's not using the finite intersection property. He's using like a characterization, like in a compact space, nested closed intervals, when you take their intersection, are not empty, assuming none of them are the empty set. And that's a problem that we did on mockqual 2, I think.
Yeah, the second mockqual 1. Yeah, it was question
sure.
3. Yeah.
Yeah.
But yes. Yeah. And so, yeah, that problem on mockqual 1, it's both you should know how to prove this problem if it's, explicitly like prove this on the qual. But that's also you should be able to just use the result of this problem, right? If it shows up in a problem somewhere. right?
Yeah, like isn't it an alternative characterization of compactness? That like if for any collection of nested non-empty closed sets, the intersection is non-empty. Is that might be a characterization? Like it's obviously we've shown that it's implied by compactness, but I
Right.
think it might be the other way around, but I've also not thought enough about it to prove it.
Yeah, I've never tried to go backwards before. The thing which I
think if you look at Vidusi's note on compact spaces, and when he like defines the finite intersection property, I think he gives that if and only if. That's helpful.
Okay. Yeah, I suppose that given any arbitrary open cover, you can like define your C1 to be the complement of one of these open sets, and then define C2 to be the complement of the union of your first open set with a new open set, and C3 as the complement of, you know, three of like you index all of your open sets. But I don't know, it feels like that only works for a countable cover instead of an arbitrary cover.
Yeah, so
So
this might not be the best way. Either way, yeah.
yeah.
It's
Anyway.
one direction is true. Who cares about the other?
Yes. Yeah. Anyway, so yeah, I go into more details on the write-up on Overleaf. Right. So like I don't say everything here because I have a write-up on Overleaf. But this is the heart of the proof. Right? You use part A to define a nested sequence.
Wait, sorry, I just want to make sure that I'm not getting this wrong. So they don't have to be nested though, right? Like the equivalent, if and only if for compact, like it just has to satisfy that if you have like that finite inner, like, well, anyway, do they have to be nested?
So for this problem, one of the things that you get from these being nested is that you can take this countable intersection instead of a finite intersection. Right.
Yeah, Catherine, yeah, you're correct. It's on Wikipedia, it says that an alternative characterization of compact space is that any collection of closed subsets with the finite intersection property has non-empty intersection. So no statement that they need to be nested.
Cool, thank you.
All right. Questions, comments, or concerns? All right. Any volunteers for question 2?
I mean, I could explain it, but I'm not sure. Like, I wasn't sure how much of this we were supposed to show, because if we assume that we know that path homotopies in B lift to path homotopies in E, then this is like a 2-line thing. But if we want to show that, then that takes some effort.
So you can see my solution. I certainly wrote more than 2 lines, but I just said, oh, by the way, this domain is simply connected, so you can't lift this, right? So for me, a lot of this problem was just like crossing the I's and dotting the T's. And the big thing is just like convincing Schultz, or sorry, this is a part A question. So convincing Vidusi that if you lift the induced path via the homotopy, that is the same as the original alpha that you started with, right? Which only requires a sentence, right? That lifts of paths are unique, and both of these are lifts of the same path, so therefore they have to be the same, right? But that is, at least for me, the only part of this problem that requires. So a lot of this work is just like hey, you have to list out the conditions, and then you have to show that those conditions are maintained. And there's like several of these. So yeah. Always avoid the urge to write a 2-line proof for your qual. Okay. Because again, the point of the qual is to prove to the committee that you understand some math. So you should be writing longer proofs than 2 lines. That being said, sorry, I don't mean to discourage you, Anthony, if you want to go ahead and give it a shot.
I mean, you having said that, I think that my answer then would not be sufficient, so I'll pass.
Okay. Is there anybody here that really wants to see a solution for 2, or should we just move on to a solution for 3? All right, then let's go ahead and move on to question 3. And Catherine and Shanna signed up for that one.
Okay, I'm gonna share my screen. Maybe. Okay, so I feel a little psyched out by this problem because all the other ones have taken me like 10 hours to solve, and for some reason this one didn't. So I'm really worried I made like a terrible mistake, but hopefully you will catch it if I did. So, okay, so we have that x is irreducible, which is if whenever x is equal to A union B and A and B are closed, then either x is A or x is B. So I guess I was thinking of this like a modified, like weaker separation of some sort. Anyway, and then so we're trying to prove that an irreducible Hausdorff space consists of at some point. So for contradiction, I assumed that there were 2 distinct points, and then using the Hausdorff condition, I put them each in their own disjoint open set, so U1 and U2. And then I kind of did what I felt like was kind of like the most obvious thing to do, is the 2 like obvious closed sets were just the complements of U1 and U2. And so that became my not separation. So because x is irreducible, then either x is one complement or the other. But if x is either of those complements, then it's not going to include x1 or it's not going to include x2, which is a contradiction. And so therefore the size of x has to be 1.
Yes, so any questions for Catherine?
Yeah, did we miss anything in here, Jacob, or is it just?
Looks
is
good to
that
me.
Fine. Okay.
Yeah, I think I was trying to do something more clever or something where I was trying to take like 1 point as a closed set and then like something else as my closed, but this is much better.
I was hoping like that I could reduce the infinite case to the finite case because I can prove it in the finite case. And I was like, maybe an irreducible space will induce that all its like any subspace is irreducible, and I couldn't show that. But yeah, that was definitely more clever than what I was doing.
Yeah, I really like your solution because it speaks to a lot of point set topology questions, which is to just do the right. I would say this a lot during my first year here, and maybe I shouldn't have because maybe it sounds kind of rude, but you should just do the only thing you can do in a lot of point set topology questions, right? So in this one, like the only thing you can do is use the Hausdorff equation, right? And then like you have 2 open sets, so make some closed sets from them. right? And yeah, and here my advice then fails because there's two ways to make closed sets. You can take their closures or you can take their complements, right? And so I guess here you just try both and one of them works really well. So you do that, right? Yeah. So point
I
set
was definitely
topology.
hung up on closures because the first problem you use closures.
All right. Cool. Well, thank you for that, Catherine. So Daly signed up for question 4, but she's not here. So I think we should skip question 4 in case she wants to talk about that on Thursday. Anyone up for question 5? I don't think someone signed up for it. So first off, what's the thing that screams out, quote unquote, to you for this problem?
Long exact sequence on relative homology.
Yeah, long exact sequence on relative homology. Cool, you've done 80% of the problem just by writing out the long exact sequence. Okay.
Yeah, the thing that I don't understand about this is like H0 counts the number of path components, right?
Yeah.
So how can it have 0 path components?
So it's relative homology.
Oh,
Right.
okay, sure.
Right. So yeah. So even though this isn't exactly what happens, because the homology has this weird kernel mod image thing, this is exactly what happens on the level of chain maps. So it's a good thing to keep in mind. For the chain maps, the chain relative homology is just the chain of your big space quotiented by the chain of your subspace. Okay. So if you fuzzily think about that in the high space, you have one path component and you mod out by one path component, and then you get the trivial group. Right? And that doesn't always work, right? Like sometimes you're like, this should be something, and then it's not, right? Because they like the one relative homology often does this, right? Like, wait a minute, how come this one relative homology is this thing? It's like, oh well, the way that these are included into the other thing induces a weird subgroup or something. But all right.
Instead of doing the proof for this problem because it's written out, can you briefly go over computing the homology of E using Meyer-Vittoris like you say you can do?
Oh yeah, sure. I think that is a great suggestion. So E is this, right? I did this on the board before I did this problem just to convince myself that I could do this before I had the audacity to write that you could do this on the thing. So you let A be this open set, and you let B be this open set. Okay. So that means that the intersection A intersect B is like this bit of the circle, right? So, hey, that means that A is homotopic to a circle, B is homotopic to a circle, and their intersection is homotopic to a single point. And this is great because then when we do Meyer-Vittoris, right, the intersection is a point. So almost all of these homologies are 0, except for the 0 case, right? The low dimensional cases, right? So you get that HQ of E is just isomorphic to HQ of a circle direct sum HQ of a circle for Q greater than or equal to 1, just from this. Or maybe this only tells you Q greater than or equal to 2. Right, because if n was equal to 1, this would be the 0 homology of a point, which is Z. So fine. 2, and then you do the normal story, right, where we do H, let's do 2 of a point goes to H2 of a circle plus H2 of a circle, which goes into H2 of E, H1 of a point. Yeah, I'm going somewhat fast through this, but that's because we spent a long time last week talking about a Meyer-Vietoris problem. And what's happening in this Meyer-Vietoris problem is easier and identical to. So you get immediately that this is Z, right? Because E has one path component. We get that this is 0 because I already said so up here. And so now we just fill in, this is Z, this is 0, this is Z plus Z, that's Z, that's 0, that's 0, 0, 0, Z plus Z. So the only question is, what is this one? And the way to look at this is to, again, look at, right, like we label some of these maps, okay, and you ask, okay, what is this I map doing? Well, this I map is sending the single path component of H into the path component of the first component and the path component for the second term. Okay, so I is injective, which implies that delta is the 0 map. And so I can replace the second row by replacing this delta with the 0 map and replacing this with 0, just like we did with the last one. And so this is an isomorphism. And so we get this is Z, direct sum Z.
For that, could you also use like the corresponding reduced sequence?
Yeah, that might be, so yeah. So yeah, you could also use the reduced homology where you just do this with respect to a point. And as I have learned since last time we have talked about this reduced homology, that's weird, that has 0 here for the 0th homology instead. Yeah, the reduced homology is just the homology of your space, comma, a point. And that's what they, when someone says the reduced homology without saying the reduced homology with respect to something, they mean the homology, yeah. The words, they mean the relative homology of the space with respect to a point. That's what they mean by the reduced homology. Or at least this is what I can tell you get from the reduced homology. But from this, you do have to have the caveat that you're computing the reduced homology, whereas this question is not asking for the reduced homology. So I don't know. It does seem like that might be easier because you might get like some more zeros here and here or something, and that might make it easier to show that these maps are injective or something, but like, yeah. Or
Yeah,
you get that this is 0 or something.
Yeah, I know I'm not fully understanding it, but like to me, the reduced homology is you take away a z essentially. So
Yeah, so we talked about this a couple of weeks ago. I think Raul brought this up, that you take away a z. And it turns out
You
that
only
when you
take it away from the end.
right, so if you do the relative homology of a space with a point, you exactly remove a z only from the zeroth homology. Okay. Because you are taking the, right, because remember that a point is the same as like a disk, right? So you're taking your path component from X, or however many path components from X that you have, and then you are modding out by one of those path components, which removes one z only from the end. Okay. And so this actually answers a question that we talked about on like week 2 or whatever we talked about this homology, that this is actually an exact sequence, because the relative homology sequence is an exact sequence, right? And that was one of the things that was unknown. So yeah, so reduced homology gets rid of a z in the 0 case, but that's exactly what you get when you do relative homology with respect to a point. But anyway, since we are doing Schultz's qual, he only cares about homology. I don't think he mentions reduced homology. If he does mention relative homology, then I'm just wrong. But you know,
I guess I've been trying to use more reduced homology in proving these, because I think that's how Hatcher approaches like the relative, like that's how he proves the relative homology of the disk with its boundary. So I've been trying to like use that same tactic, I guess.
yeah, that's totally fine. Schultz has been around long enough that if you compute the reduced homology instead of, right, instead, he'll probably be like, oh yeah, that's still fine, right? I've just been focusing on homology as opposed to reduced homology, because that's what I think Schultz is going to be asking. Okay? Cool. All right, any other questions, comments, concerns, or complaints for question 5? I'll take them. All right. Then let's go ahead and move on to question 6, which I think was also signed up for, yeah, by Shannon Catherine.
Okay, I'll take this one. Okay. So funny, this definition of simplex really got us. Apparently, right, the tetrahedron is solid. Apparently, a face does not just have to be an n-1 dimensional simplex, right? So it can be, if you have a 2 simplex, a face can be a vertex, it can be a 1 simplex. So we had to be real careful with that. So after like 10 hours of that, let us know what you think about this one. So we have A is a simplex, B is a union of faces of A. Again, they don't say 0 faces, 1 faces, they just say faces. So we just went with that. We need to prove that the Qth homology of B is, you know, that somehow you can get that to be the Q+1 homology of A and B for Q greater than 0. And then we want to provide a counterexample for Q equal to 0, where A is a 1 simplex. I think there's a couple ways to do that one, but see if you like this one. Okay, so we need a definition. So an N simplex, it's the smallest convex set in Rm containing the n+1 points, V0 to Vn. So I think this is the key, that up to homeomorphism is zero simplex is homeomorphic to or a D0 disk. A 1 simplex is homeomorphic to a D1 disk. A 2 simplex is homeomorphic to D2, and a 3 simplex is homeomorphic to D3, which is pretty awesome. So a face of an N simplex is going to be the subsimplex with vertices any non-empty subset of the VIs. We had a note to ask you because in a lot of definitions they say a face is any non-empty subset of the VIs because of this, like you can have a 0 face, 1 face, things like that. That's just an example. Okay, so we're going to use the long exact sequence here and compute HQ plus 1B, HQ plus 1A, HQ plus 1AB, all the way down. So for Q greater than 0, we get HQ plus 1 of A is 0 because the N simplex is homeomorphic to Dn. You get the same thing for HQ of A. So if we can put our maps together, we got the kernel of G. Where's our G? Right here. Is the image of F, which is 0. So G is injective. We also get the image of G as the kernel of H. And that is the Qth homology of B, so that G is surjective. So we get G as an isomorphism from this. And that's our part A. So for a counterexample, we take A to be a 1 simplex. We're really fond of excision. We're like, we're going to use this on everything. So the conditions for excision is to take Z, a subset of A, subset of X, where the closure of Z is in the interior of A. Excision says to compute the homology of X take away Z, A take away Z, and that this is isomorphic to H XA. So we say, okay, let's take, so again, you want A to be a 1 simplex and B to be a union of faces. So we say, all right, let's take B to be the union of these 2 0 simplexes. So I don't know why we changed notation, but just say Z is B for the interest of excision in our problem. So A looks like this, Z looks like this. So if we actually take H1 of A take away B and B take away B, again, that's supposed to look like X take away Z, A take away Z. This by excision is isomorphic to H1AB. So B take away B is just the empty set. And so you get this H1AB should be isomorphic to 0. So if we compute a snippet of this long exact sequence for H1A take away B0, empty set, and H0 of the empty set, the H1 of A is 0. Again, from the reasons above, homology of the empty set, 0th homology of the empty set is 0. And so we get the image of F is the kernel of G, image of F is just 0. And so this H1 A take away B empty set is 0. But, you know, H of 0 of B was Z direct sum Z. So this is a counterexample, and our big picture idea is that for Q greater than 0B is always path connected, but for Q equals 0, perhaps not. Is there another clever way of doing a B, or is that one all right?
I just have one thing that I didn't follow. You said in that line, second line under, you say H1A minus B relative to the empty set. Sorry, I guess third line. You somehow say that that's isomorphic to 0. I'm not sure how. Like I believe it. I don't know how you get that.
From here? From image kernel, is that what you're saying?
Oh, okay. So that I thought you were using.
Yeah.
Okay, so you're going in the other direction.
Oh,
My
sorry,
bad.
a little backwards there. Yeah. I think
Okay.
we were trying to put the results like right here or something. Yeah, sorry about that.
No worries.
Mhm. think excision is awesome, but if you don't use the right Z, everything falls apart, right? Right, Catherine?
I agree entirely with that statement.
Like, what is this
Although,
thing?
actually, was excision valid here? Because it,
Hmm.
oh wait, no. Yes, when you're only dealing with simplexes, you can do this. When you're dealing with general spaces, you have to care about openness. Never mind.
Mhm.
Yeah, this even works with openness, but yeah, you're right. So that is one thing. So here, this is excision in general. But excision for simplexes, you don't have to worry about the closure or the interior condition. You could just take.
Sorry, we did try to satisfy that though. Was that not satisfied?
No, it is satisfied here. Yeah.
Okay.
Because A is your entire space, so it's open. So the interior of A is itself. And right, Z is just a union of faces, so it's closed. But it turns out that as long as what you're dealing with are faces of a simplex, the interior is close enough to your simplex, and the closure is always itself. So
Yeah, and my
you kind of get
my
these for
thought
free.
was just the only time I ever use excision is with everything being open. And that doesn't work here, obviously, but that's a special case of excision.
Yeah, is there another way to get a counterexample without excision, Jacob? Or
So the counterexample that I was thinking of was the exact same counterexample. I just didn't use excision to compute it. Okay. I just built the long exact sequence with this example, and then I just used the Meyer-Vitor sequence, and I looked at the maps, and I found that one of them was Z plus Z and the other one was 0, and I got the same answer. Yeah, so I used the exact same counterexample except that I can use excision. But it looks like that excision is a little easier to do because I had to like write out the Meyer-Vitor sequence and like show that like this map was injective, and so therefore this thing was 0, and like do the whole shebang to like get the thing that I wanted, right? Yeah.
yay.
Cool, thanks. Were there any other questions for Shanna? All right, let's go ahead and move on to question 7, I suppose. So if I recall, Anthony signed up for question 7. Great.
I took a page out of Vidor's book and put this in a Beamer. So let's see.
Sorry,
Whoops.
sorry to interrupt. One quick question about the previous one. Could you do it even simpler with just take a point and do homology relative to that point? Because then H0 of a point is Z, but H0, or sorry, H1 of the empty set is nothing, right? It's 0, right? And if you do H1, or if you do homology of thing minus everything,
Yeah,
it should be 0.
it should be 0. Yes, that is a valid counterexample. However, the problem specifically says using a1 simplex.
Oh, and a
Yeah.
point is
A
unfortunately
point is
not
a 0
one
simplex. Yeah. So yes, that is a counterexample to the statement.
Well, then
but it's not the counterexample that the question.
I mean, so then just like, fatten up the point, do an interval, and then do the homology relative to said interval. Would that still work? Because you have one path component, so H0 of the interval is Z.
Yeah,
and then
so
again,
this
you just
was
delete everything.
one thing that I was gonna say. So Shanna said that she looked this up and that a face is just any face generated by any subcollection of vertices. I always thought the way that, and this the convention that I learned is probably different from the one that Shanna found. I thought that the convention for face was that they were the one dimension lower simplices,
Mhm.
not just any subsimplex. I thought that they were one dimension lower. So yeah, I think that if you used A equals B here, that would be fine. I would just use the version with the points just in case they were like, no, a face is an n-1 simplex, and then you get dinged because your B wasn't actually a union of faces the way that I think it's probably fine, like, because Schultz is not the kind of person who cares about minutia, at least from my experience. As long as you write, right, we define a face to be any sub-collection of, then you could probably just let A be an interval and B be the entire interval and then do that instead. But the counterexample that I certainly was thinking was where you had two distinct points on the edge. Because that's kind of what goes wrong, quote unquote, at least in the definition of faces that I was using. Anytime you have a simplex, if you take any collection of n-1 faces, they're always connected by an edge, right? But this fails for a single one simplex when you take 0 faces, because then you get disjoint points. But yeah, this might just fail in general, even if you take a higher dimensional simplex with faces at 0. I don't know. I haven't done it for 2 simplex or 3 simplex. Yeah. So I don't know. Long story short, yes, I think that example works, and I don't see any technical reason why it should be wrong, besides convention, which isn't a good reason for things to be wrong.
Yeah, no, I was just checking because I was trying to figure out if I understood the proof.
All right, take it away, Anthony.
Okay, so we want to show that the solution set for this equation is a smooth manifold, and we're going to do this using the regular level set theorem. So we're going to let F be the map defined by the left-hand side here. Oops. Clearly this is smooth. It has partial differentials, continuous partial differentials of all orders. Suppose we have a critical point of F. So recall that a critical point is a point where the differential is not surjective. So in this case, that means that the rank of the differential is less than the dimension of the codomain, which is R. So that forces that the differential has to be 0. So we look at a matrix that represents the differential, taking the standard smooth structure on R3 and R. That's the Jacobian matrix. So the entries for the Jacobian matrices are just the partials of F. So we have that this matrix has rank 0, so it's the 0 matrix. So we can write each of the entries 0. So now let's look at the different cases here. If 1 minus Z naught is 0, then well, one of the terms in F becomes 0, so F is 0. Otherwise, this E equation implies that X naught equals Y naught, right? So we have 1 minus X squared 0 is 0, is non-zero, so we can cancel. And we get X0 equals Y0 equals 0, which means that X0 squared plus Y0 squared is 0. So then this term becomes 0. So F of P is 0. So this means that if P is a critical point, then P is in the level set of 0. So the only critical value of F is 0. So in particular, 1 is not a critical value, it's a regular value. So the level set of 1 is a regular level set, which makes it into a embedded submanifold of R3. In particular, it's a smooth manifold. And that's it. Any questions?
Very nice. That's slightly smoother than mine. I immediately set up my, like, for contradiction, assume that one of these points is a critical value. And then just got that, like, wait, that means that this point is not the pre-image of 1. But yeah, I think that's a little nicer. All right. Would anybody like to talk about question 8?
Again, I can do half of 8, maybe. In like one line, I think you can say that that delta M is a smooth submanifold by considering it as the 0 level set of the distance squared function from M cross M to R. Now, that does not help you with the rest of it, but it was an interesting way to look at it, I thought.
Yeah, so for that one, you need to have an additional fact that says, like, every smooth, that, like, you need to be able to say that M has a metric on it, but this is true, right? Every smooth manifold is metrizable, and so you can just impose a metric on the manifold and then do this, and that is a valid way to complete the proof, because what you get, no, hold on. No, somewhere this breaks. The distance function is not, 0 is not a regular value of the distance function.
Even of the distance squared to get rid of the singularity.
Even of the distance squared.
Yeah.
Yeah, because
well.
Anytime you have your 2 points being the same, you get a 0 in your Jacobian. But when the distances are different, you get a non-zero in your Jacobian. So you get a lot of zeros in your, yeah, so you don't have constant rank in your Jacobian. And it's a good thing that it doesn't work here, because then this problem would be wrong. Then, like, so if the dimension of M is M, right, little m instead of capital M, if the regular level set theorem was right, then this would be a 2m minus 1 embedded submanifold. But hopefully you would agree that the function which takes M to M cross M here, and I'll write this part out just to, you know, be better. Let's share this notebook, right? Hopefully you would agree without me spending much time doing this, which just sends M. We'll do P since I already declared that to be P comma P, right? That this is smooth. And if I restrict this to delta M, that this is a diffeo. Right, because it is just the identity in each coordinate, right? The identity is certainly smooth, right? You can show that this is injective and surjective. The inverse is just going to be, you know, you choose one coordinate and that's fine. right? So this is certainly a diffeomorphism, right? So that means that delta M should be little m dimensional. But if the regular level set theorem argument worked, then you would get that this is 2m minus 1 dimensional. And you don't want that. that would break math. But essentially, this is the extent of the proof, right? Since this is m dimensional, that means that its tangent planes are m dimensional. Okay. And the normal planes are 2m minus m dimensional, which means that they're m dimensional. And linear subspaces are isomorphic if and only if they have the same dimension. Okay. So that means that the normal tangent planes are isomorphic to the normal, the normal planes are isomorphic to the tangent planes, and then you stitch together the tangent planes to get the tangent bundle, and you stitch together the normal planes to get the normal bundle, and you end up doubling the dimension for each of these things in both cases. And so again, the dimensions of the two dimensions are the same, so therefore they are isomorphic. Like I said, I didn't write out solutions to this one, so I don't know what the details are, but that's because, you know, this one was one of your finals, so I thought that one of you would have the details to this one. But this is the roadmap, which I can at least provide. Right? Is that once you know that this is an m-dimensional manifold sitting in a 2m dimensional space, right? The rest of that just follows. And in case you forgot what the normal planes are, right? You take the tangent plane at P of m cross m. And so the normal bundle at P of delta m is equal to the set of all V in this, such that V is orthogonal to the tangent plane of the diagonal. Right, that's the normal bundle. You just choose a dot product on your tangent plane, and then you just take all of the ones which are orthogonal, and that's the normal. So if I were Fred, and I was doing the thing that Fred normally does, where I choose a subset of the final exam problems to put on the qual, I would probably choose the final exam problems that people did not answer on the final and put those on the qual. So the fact that nobody here was able to answer this problem tells me that this was probably a lower picked problem. So I would invest into learning this problem for the qual and then reviewing all of the 8 other problems on his final. But you know,
If we can't get it, could we ask you kind of for a more fleshed out roadmap on Thursday?
Yes, but I haven't done it either. So my more fleshed out roadmap would just be me writing more of these definitions down, probably in better formality. Are there any other questions about 8, such as it is?
Does this roadmap, sorry, I was like multitasking. So this roadmap shows that the tangent and normal bundles are isomorphic because, well, the tangent plane is m-dimensional because like how many other dimensions can you move in tangent to this? And then the normal plane is to fill out the 2m. But does it show that it's a smooth submanifold?
Yeah, so this is a diffeomorphism. It's a restriction of this smooth map. therefore it has constant rank, because diffeomorphisms have constant rank. Okay? And so therefore this is a smooth embedding. And that shows that it's a smooth submanifold.
Awesome.
Great question. I totally forgot to mention that. All right, anything else? Okay, then I think we have just enough time to go over question 9, which was signed up for by Shannon Catherine.
Okay, Jacob said to sign up for lots, so I trust Jacob completely, so that's what I did. So I think there's a lot of calculus in this problem, which sadly was what took me so long, but anyway, so what we're trying to show here is that if you apply this particular vector field to a function, the same as just multiplying it by the constant if your function is, oh, I'm totally forgetting. It's homogeneous of degree C, or positively homogeneous of degree C, which is this definition up here. So I guess very briefly, like just to convince myself that this question made sense. Sorry, so this vector field here basically takes your partial derivative and then multiplies by the corresponding xi. So I just used a simple example here just to like convince myself that that made sense, that that would indeed happen that way. So basically, if you have a very simple like polynomial like this, what happens is the partial derivative like kills one of your terms, and then the term gets multiplied back. So obviously, like there's another example here that's a lot more complicated and it's not as obvious, but like at least it makes sense that this should indeed happen. So anyway, the actual proof, you can define this function g of x lambda in this way. And then it seems like the trick is to take a partial derivative here with respect to lambda. And so then if you do that and basically use the chain rule, I also tried to be careful and like switch my variables, but basically it's an application of the chain rule. Then you get exactly what you want. Don't really know if there's like a lot more to say about this one.
Yeah, so morally, and I write the word morally in my solution, which maybe isn't a good word for math. If you look at this E sub x, right, this vector field E sub x, right, this is the vector field which points in the direction of x with the same magnitude as x, right? Because it has length component of x in direction that component of x, right? So that means that when I take the derivative of a vector, of a function with respect to this vector field, right, I'm taking the derivative of the function in the direction of the vector that I plug into the function. But what happens when I take the derivative of this function with respect to lambda, right? Well, the lambda times a vector also gives me a derivative of that vector in the direction of that vector. Because as I move lambda up and down, I'm just scaling my vector in that same direction. So that's morally why the trick of take the derivative with respect to lambda should work. Because if I take the vector field and apply it to the function, I'm taking the derivative with respect to the direction of the vector I plug in. And when I take the derivative with respect to lambda, I am having a derivative in the same direction as the direction that the vector field gives me. Okay. So this is like the inspiration, quote unquote, that I didn't have. Like, I think that the solution to this problem has been passed down through generations, because I don't think that this is obvious at all. But that's supposed to be what the inspiration behind taking the derivative with respect to lambda is that you try to see that, oh, the derivative of this vector field is the same as this one-dimensional derivative, and it's a lot easier to wrap your hands around a one-dimensional derivative. And then there's like a double chain rule, and like this answer just seems to like pop out of the woodwork from nowhere. But because of the thing that I just said, maybe we shouldn't be surprised.
Okay, yeah, thank you, because I didn't understand. I was convinced it did work, but I didn't really understand conceptually why. So yeah.
So if you look on the overview file, I also wrote out my solution to this, but it is morally the same. You take a lambda derivative of the same g, and you do the chain rule a couple of times, and then you pop out the answer at the end. So if you'd like to read this or reference this back, it's on this file. And I felt bad about this because I was like, oh, I put this question 9 on this mock qual, and that's because this is one of those problems that has shown up on old like Fred exams and also his quals, so I should put it on here so that we all know how to do this problem. And then I was like, well, I'll just copy it on the solution since I already have it written from when I took the qual in 2019. And then after that, I noticed that you guys signed up to do this problem, and I was like, oh no, I'm so sorry. So next time I won't do that. I'll wait until people sign up, and then I'll start putting solutions. Okay, cool. So next time we'll give Daly the chance to present question 4 if she's here. If she's not here, then maybe I can present on question 4. And then since we only have one question, I was not expecting that it would take us only one day to get through essentially all 9 problems, or most of 9 problems. So I don't know, maybe Thursday would be a good day to like go back and hit some problems that we missed from like past mock quals and exercises to know, or you all can find problems from the old qualifying exams that maybe y'all want to talk about, and we'll have it be more of like a, less of like a we're doing these problems kind of day, more like a free form kind of day, if that sounds all right with you. If y'all have suggestions or problems that you would like me to look at before Thursday, feel free to email them to me beforehand and I'll take a look. And if you have questions now, feel free to ask, but I'm going to stop the recording, and if you'd like to go now, you can.